Good morning, ladies and gentlemen. Thank you all for coming. I'm going to be talking about a new method of assessing beta diversity. So, ever since the seminal paper of Whittaker, diversity has been discussed in terms of alpha, beta, and gamma diversity. Gamma diversity is the total richness of an assemblage and is influenced by alpha diversity, that is the richness within each locality or habitat, and beta diversity, which is the taxonomic differentiation between the localities. Beta diversity is normally assessed as a set of pairwise taxonomic distances between the localities. There's a huge variety of metrics you can use. I'm just going to give a couple of examples of the equations, but they all work on pretty much the same principle, comparing the number of species shared between the localities to the total number of species in each locality. A distance of 0 indicates all species are shared between the localities. A distance of 1 indicates none are. Now, when you're assessing any macroevolutionary pattern, particularly in the fossil record, you need to account for the fact that your sample is incomplete, and beta diversity is no exception. If we have here a homogeneous fauna, two localities with the same set of taxa, so a true beta diversity of 0, and we then incompletely sample this, we won't necessarily find the same set of taxa in each locality, and our beta diversity estimate will be raised. If we make our sample even more incomplete, the less likely it is that we will sample the same set of taxa, and the higher our beta diversity will be pushed. So if we're comparing, say, two time bins that are sampled heterogeneously, the results will not be directly comparable. Now, all of what I've just said is old news. The need for sampling standardization in beta diversity is long established, but there is one issue that hasn't been very heavily discussed in terms of beta diversity, and that is the influence of the abundances of the taxa. Simply put, it is easier to sample abundant taxa even at quite low levels of sampling, whereas you have to sample much harder to get the rare taxa. This has been long discussed as a bias in alpha and gamma diversity studies. It's the reason why rarefaction curves have different shapes and cross each other. But how does it affect beta diversity? If we have our homogeneous fauna with one very abundant distribution, a very uneven abundance distribution, the one very abundant taxon is likely to be sampled in both localities. So this acts to keep our beta diversity estimate low. If we have a more even relative abundance distribution, no hyperabundant taxon, it is more likely we will sample different sets of taxa in each locality, and our beta diversity estimate will be pushed up. So again, if we're comparing two time bins, even if the sampling is the same, if they have different abundance distributions, the results will still not be directly comparable. So what I'm going to do today is first use a combination of simulations and empirical data to demonstrate that this actually is a problem, and then propose a solution. So my simulations, as I showed you before, two localities within a homogeneous fauna, same set of taxa that are incompletely sampled. I control the evenness of the abundance distribution by sampling the number of specimens from each taxon from a log normal distribution, whose variance controls the evenness. A higher variance is a lower evenness. So since these are homogeneous faunas, their beta diversity is 0, so when we compare beta diversity to evenness, what we should see is a flat regression line as close to 0 as possible. What we actually see is a strong correlation between our observed beta diversity and evenness, and the worse our sampling gets, the stronger the correlation and the steeper the regression line. So what the problem we're dealing with here is that the null expectation, that is the beta diversity value you would expect were you to sample a homogeneous fauna as incompletely as your observed fauna, will differ from time bin to time bin. So how does this affect an actual empirical data set? As an example, I'm using the Karoo Basin of South Africa. One of the best records we have of tetrapods across the Permo-Triassic boundary. We have thousands of specimens, well-established biostratigraphy, recently correlated to radiometric dates. And over the past few years, my colleagues in South Africa have been assembling data on the specimens with an up-to-date taxonomy and locality data. So for each of the biostratigraphic assemblage zones, I compiled a list of the specimens that have a reliable taxonomic affinity and used these to generate the relative abundance distribution. I then emptied the specimens from the dataset and refilled them at random from drawing from the abundance distribution of that biostratigraphic assemblage zone. Those are the time bins. I'm going to be using. So since the specimens from each locality in that assemblage zone are being drawn from the same abundance distribution, what I'm effectively doing is simulating a homogeneous fauna sampled to the same extent as that assemblage zone. So if I do that 100 times for each assemblage zone and calculate the beta diversity of the resulting assemblages, again we should see a flat line close to 0. But with all metrics tested, we see quite substantial variation. Even the Bray-Curtis metric, which actually quite surprised me because it works on abundance data rather than presence-absence data. The simulated beta diversity correlates strongly with evenness measured using the EVAR metric, and if you standardize your sampling by coverage, this doesn't change. So, as I said, what I've effectively simulated here is the null expectation of your beta diversity study, what you would expect were you sampling a homogeneous fauna as incompletely as your observed data. So if we compare our null to the actual empirical observed beta diversity through time, we see something slightly troubling. The major shift in beta diversity, this dip towards the end of the middle Permian, which looks like an episode of cosmopolitanism, is actually just our observed beta diversity tracking the null expectation. This is a bit problematic. It's particularly problematic when you consider the context in which many of these beta diversity studies are written, comparing major shifts in beta diversity to major events like mass extinctions, radiations, and the such like. The problem is that this is the times when we see major changes in the shape of the relative abundance distribution, for example, the prevalence of pioneer taxa and disaster taxa. So when we see decrease in beta diversity across a mass extinction, are we really seeing an episode of cosmopolitanism, or are we just seeing the null shifting down because of the increased unevenness of the fauna? So what's the solution? Instead of treating 0 as the null, you need to calculate the null, perhaps using the same set of simulations as I showed you for the Karoo, and then see how far above the null your observed beta diversity estimate is, rather than how far above 0 it is. So we have a beta diversity scale from 0 to 1. We have an observed beta diversity value calculated using your preferred metric, and we have a null calculated using the same method I showed you on the Karoo data. Now, if you just subtract the null from the observed, you shift 0 to the null, which is what you want, but you also shift the maximum obtainable value to 1 minus the null. So that's not ideal. So you need to rescale the values so that 0 is at the null, 1 is the maximum, and your beta diversity is here. I call this the relative abundance corrected beta diversity, or RAC. So how does it perform? Well, in the same set of simulations I showed you before, the two homogeneous localities, when we sample at 10%, the regression line between RAC beta diversity and evenness, that's the blue line, is almost flat and is closer to 0 than the raw beta diversity. So that's what we want to see. I also did a set of time series simulations where I had a different provinciality and a different shape abundance distribution in each time bin, and I then calculated beta diversity using the RAC method and the raw method and did the correlations between these two time series and the true time series, and the correlations of the RAC method are significantly better than the raw method. If we drop sampling down to 5%, we do start seeing an increased slope of the regression line of the RAC method, but it is still outperforming the raw beta diversity method, and the correlation between the RAC time series and the true time series is still significantly better. So how does this method perform when you start violating its assumptions? One of the assumptions that I'm sure a lot of you are thinking about is that the simulations assume the observed abundance distribution is correct. And obviously in the fossil record, that is not an ideal assumption. We have plenty of examples of formations that selectively preserve larger taxa, smaller taxa, calcitic taxa, aragonitic taxa. So if we have, for example, a formation that selectively preserves the larger taxa, our observed abundance distribution will be wrong. So to see how the RAC method performs under these circumstances, instead of each individual having a sampling probability of 10%, I drew the sampling probability of each taxon from a normal distribution. So each taxon would have a different preservation potential, producing an incorrect abundance distribution. Even so, it still performs rather well. The, again, regression line between the RAC beta diversity and evenness is almost flat, and the correlation between the RAC time series and the true time series is still significantly better. This is perhaps not as surprising as it might seem. If you have a formation that selectively preserves larger taxa, one very large taxon will have the same effect as one very abundant taxon would in a situation where preservation potential was equal. Where the method starts to fall down a bit is if you have different preservation potentials for your different localities. If you have one, say, that selectively preserves the larger taxa, and one, perhaps more Lagerstätten-like, that selectively preserves the smaller taxa. There we lose the significant outperformance of the RAC method over raw beta diversity. It doesn't perform worse. In fact, I simulated quite a wide variety of sampling regimes, and I never found one where the RAC method performs worse than the raw beta diversity. I just found ones where it doesn't perform significantly better. So to a certain extent, this makes the crew quite a good test subject for the RAC method, as it is a single basin with a relatively consistent mode of preservation during the Permian and Triassic time bins. So just to finish, I'm going to look at the RAC beta diversity of the Karoo through time. The solid black line is with subsampling, standardizing by coverage. The dashed line is without subsampling. And both curves indicate an increase in beta diversity across the Permo-Triassic boundary. This contradicts recent studies that have suggested increased cosmopolitanism at this time. Now, it is entirely possible that the difference is due to the fact that I'm looking at a more local scale. But one thing that does need to be considered is the increased unevenness of the abundances across the Permo-Triassic boundary, the prevalence of disaster taxon Lystrosaurus. So is this what has been driving the signals seen in previous studies? That's something that needs to be looked at in future. With all that said, I'll just thank all these people for data, for helpful comments and discussion, and of course for money. And thank you all for listening.